Hi all. Today in this lecture, we are going to learn the race around condition and master slave JK flip flop. Okay. What is a race around condition? It is a commonly asked question in university question papers. So consider a JK flip flop. Okay. For a JK flip flop, if J is equal to K is equal to 1, and also if the width of the clock pulse TP is too long, then the state of the flip-flop will keep on changing from 0 to 1, 1 to 0, 0 to 1 and so on. So at the end of the clock pulse, we cannot predict the output of the flip-flop. Okay, and we know that when J is equal to K is equal to 1, the state of the flip-flop will be toggle. That is, if the previous output was 0, then it will changes to 1. If the previous output was 1, it will changes to 0. But in this condition, if the width of the clock pulse is too long, we cannot predict the output. Okay, so just take an example of a normal JK flip flop. Our normal JK flip flop. So this is the figure of a normal JK flip flop. Okay, and suppose if J is equal to 1 and K is equal to 1 and our present output is 0, that is Q is 0 and Q bar is 1. Okay. So for the better operation of this flip-flop, this clock pulse, the width of the clock pulse should be too short. Okay. It should be a just peak-like structure. Okay. Then only the flip-flop will actually work. That is, for J is equal to 1 and K is equal to 1. After applying this clock pulse, we know that the output of the flip-flop will changes to, that is toggle. Output will toggle. That is 0 changes to 1. That is Q bar will become 0. Okay. So this will be the present output of the flow, that is Q will be 1, Q bar will be 0 after applying first clock pulse. Okay, this is the normal condition, and here the race around condition is that here we are assuming that the width of the clock pulse is too long. Okay, width of the clock pulse is too long, that is it is like that. Okay, and also we know that for this type of gates, for all the logical gates, there is a certain propagation delay. That is, if you are giving an input to a gate, there is some delay for getting the output. Okay, so this propagation delay is there for any digital logic gates. Okay, so after applying the inputs, so in this circuit will take some time to produce it output. Okay, and if this the width of the clock pulse is too long, that is if it is greater than the entire propagation delay of our circuit, we can't predict the output of the flip flop. Okay, it will keep on changing from 0 to 1 and 1 to 0, etc. Okay, that is, suppose if J is equal to 1 and K is equal to 1 and Q is equal to 0 and Q bar is 1. Okay, it is a present condition. After applying the clock pulse, after applying this first, that is first we are considering it as a positive edge triggered one. So at the time of first edge triggered, the output of the flip flop will toggle, that is it will become 1 and it become 0. Q will become 1 and Q bar will become 0. Okay, and we know that the width of the clock pulse is too long, that is it is same, it will continue as 1. Okay, so the clock pulse is still it is 1, so the output of the flip flop again changes from 1 to 0 and 0 to 1, like that. So we can't predict the actual output of that flip flop. So this condition can be overcome by a master slave flip flop. Okay, a master slave flip flop. So a master slave flip flop is developed to make the synchronous operation more predictable. That is, the race around condition can be avoided by introducing a non-time delay. That is, this time delay will be equal to the width of one clock pulse. Okay, so here we are introducing a non-time delay between the time that the flip flop responds to a clock pulse and the time the response appears at its output. So here we are introducing a time delay between the flip-flop response to the clock pulse, okay, and the time the response appears at its output. That is, the response appears at its output. It is based on the propagation delay of the gates, okay. So the master slave flip flop contains two flip flop, that is a master flip flop and a slave flip flop. Two flip flops will be there. Okay, so the control inputs are applied to the master flip flop on the rising edge of the clock pulse, and the levels on the control inputs are used to determine the output of the master. Okay, so here we are applying. So here we are applying the clock pulse. Okay, if it is too long, so the control inputs are, okay, first the control clock pulse is used to generate the output of the master flip flop, okay, and on the falling edge of the state of the, that is the falling edge of the clock pulse, the state of the master is transferred to the slave. Okay, so here you can see a master slave JK flip flop. Okay, so this is the master and this is the slave. So if this is the clock pulse, okay, if this is the clock pulse, at the rising edge of the clock pulse, the output of the master will be here. Okay, that is the clock pulse is given here, and the clock pulse of the master, the clock pulse of the slave, this is the clock pulse of the slave flip flop. It is given through a NOT gate. So clock bar is given to the slave. Okay, so at the rising edge of the clock pulse, the output of the master will produce an output, and at the falling edge of the clock pulse, then only the slave flip flop will inactive. Okay, so at the rising edge, this slave flip flop will be in inactive condition. Only the master will be inactive, and it will produce its output, and this output is transferred as our actual output. That is, our output is transferred to the slave only at the falling edge of the clock pulse. Okay, then we will get a correct output at Q and Q bar. So during this long time period, the output of the last output Q and Q bar will not keep on changing. Okay, so only after the negative falling edge of the clock pulse, the slave produces an output. It will be the actual output of our flip flop. So this is the actual working of the JK master slave flip flop. So this is the representation of a JK master slave flip flop. So for representing master slave, here we are using a symbol like this. Okay, and the master slave JK flip flop, we have already discussed about the master slave JK flip flop. So for the master slave JK flip flop, the JK flip flop is followed by an SR flip flop. Okay, this is the JK flip flop. It is followed by an SR flip flop here. Okay, and there is the master flip flop is a JK flip flop, and the slave flip flop is an SR flip flop. Okay, so here the master flip flop we are using a JK flip flop, and the slave we are using an SR flip flop. So enter the circuit will be our master slave JK flip flop. So this enter circuit we are commonly using in our circuits. And also here you can see the preset bar and clear bar symbols. Always for clocked operation, this preset and clear bar should be 1 1. Okay, and this is the truth table of a JK master flip flop. It is same as our we have already learned the truth table of a JK flip flop. That is for 0 0, the output will be will not change, no change condition either. For 0 1 output will be in reset condition, that is output always will be 0, and for 1 0 output will be 1, that is set condition. For 1 1 output will toggle, that is q 0 bar. Okay, so that's about our raise around condition and master slave JK flip flop. Thank you.